Hello, everyone. What I want to do now is go over section 3.4 on subsequences. I'm not going to go over everything there now. I'm going to leave lim sup and lim inf for another time, maybe another video, or depending on how long this is, maybe for Wednesday, we'll see. But yeah, I do want to do lim sup and lim inf separately. I want to do it nice and slowly because it's a very important topic, not necessarily for this course, but for more advanced courses. For example, 510A, there are very deep theorems just that you can't state without lim-infs and lim-sups, particularly lim-infs and something called Fetou's lemma. But in other courses, and really algebra, analysis, and topology, um, and we'll get into this more, but whenever you have a bounded sequence of numbers, uh, and you still want to associate a natural limit to that, even though the sequence itself might not be convergent, the way to do that is generally using lim-infs and lim-sups. Okay. So, yeah, so we're going to be talking about subsequences. Okay. And I'll talk a little bit more about divergent sequences in this section too. Okay, so what is a subsequence? Well, it's very simple. It's basically what you would think it is. Let's say I have integers n1, n2, etc., etc. So, yeah, these are all integers, and they're strictly increasing. Let's say they're positive integers. So in particular, this could n1 could be 1, n2 could be 2, n3 could be 3. That's certainly a possibility, but we just require that this be strictly increasing. Okay? Um, so the definition of a subsequence is simply just looking at these elements here. So x and 1. So again, n1 could be 1, n2 could be 2, etc., etc. So the original sequence is itself a subsequence of my sequence here. So maybe to be more clear, let's say I'm starting off with a sequence xn. So this is called a subsequence. So maybe the simplest example of a subsequence is the m tail for any positive integer n. So write this out, x, so it looks a little neater, put the m first, but m plus 1, m plus 2, etc., etc. Okay. So this satisfies the condition of a subsequence. This is n1, this is a positive integer. So this is, of course, m is a positive integer itself. So we have positive integers n1, n2, n3, etc., and n1 is less than n2 is less than n3. It's strict inequalities. Okay. Another simple example would be just taking the even indices for a sequence or doing the odd indices. So, for example, let's do the odd ones. So this is x. Let's do, sorry. We could do this. Let's instead do all of the odd integers, positive odd integers. So This is x1, x3, x5, etc. So my n1 here, n1 is 1, n2 is 3, n3 is 5, etc., etc. So this is a subsequence. On the other hand, just kind of, not that we probably need to do this example, but let's say I have the sequence 1 over n equals 1 to infinity. So something like this, 1, 0, 1/3. I think this is actually in the book. This is not a subsequence. I mean, intuitively, a subsequence is like a subset of my original sequence, with the small caveat that we must have indices strictly increasing. But you basically should think intuitively that a subsequence is like a subset of my original sequence. So this is not a subsequence of this sequence here. I mean, there's no 0 in the sequence here, so this is you can't write this as xn2 for uh xn being for xn2 being something in the sequence. You can't write 0 as 1 over n for any n. So okay, so enough of the examples, because really conceptually subsequences are very simple. A whole hell of a lot to them. So the first theorem is kind of trivial, but it's still important, as we'll see. Really call this a proposition, but all right. So if xn converges to x, then any subsequence also converges to x. And of course, this is a subsequence of, so k equals 1 to infinity. Running out of room here, but this k equals 1 to infinity. So this is, of course, a subsequence of xn. So one thing I want to point out, basically, this is very easy by induction to prove. If you have any doubts, just prove it. And that is, I mean, it's obvious, but for any k, nk is bigger or equal to k. It could be equal to k, like I said many times before. N1 could be 1, N2 could be 2, N3 could be 3. You could then have N4 is 10. That's fine. But just because these are all positive integers, and it's strictly increasing, that forces nk to be bigger or equal to k. That's important for this theorem. So how do we prove this? It's a very easy. Pick epsilon bigger than 0. Pick k. So I'm doing using k here, so I'll use capital K. Put these little things here. So pick k, an integer k, where positive integer k, or for any n bigger than k. Xn minus x is less than epsilon. But k, little k, sorry. nk is bigger or equal to k. This is a little k. So as for all natural numbers k. So this k also works for my subsequence. As long as k is bigger than big K, then nk is bigger or equal to k. All right, so let's do an example to illustrate this result and illustrate how this is useful. Okay, so in particular, let's say b is between 0 and 1. So what I want to do is prove that this limit here, sorry. This limit here is going to be 0. Okay. Okay. So remember, or I mentioned that the book proves this in the first section, section 3.1 of the of limits, and they use it using kind of like the homework, the binomial theorem. But let's do it in a different way here. Okay. So first of all, trivially, Bn is positive for all natural numbers n. So 0 is a lower bound. This is fairly clearly decreasing. This b is between 0 and 1. Everything's positive here. So this is strictly less than b to the n. Again, because b is between 0 and 1. Okay, so the limit exists. The monotone convergence theorem. Let's say x is this limit as n goes to infinity. Sorry, not xn, bn. And I claim that this has to be 0. Okay, so let's see why this is true. There's different ways to do this. Probably the simplest way to do it is the following. Okay, so x is this limit. Sorry. This is b raised to the n. There is no such thing as b sub n here. Okay, so this is going to be equal to, let's just take the subsequence involving even terms. Okay. That's a perfectly fine subsequence. Well, this is really b to the n, whole thing squared, so this is the same thing as by the limit laws. Okay. And so this is going to be x squared. So x is x squared. That's the same thing as saying x squared minus x is 0. X is 0. or x equals 1. Okay, so let's eliminate x equals 1. How do we do that? That's easy. So because b is between 0 and 1, b to the n is less than b, you could just bring bn to the right-hand side and factor out a b, see that. And this is less than 1. So that means the limit here, well, by that limit law for inequalities, all we know is that this limit here is less than or equal to b. We don't know that it's less than b, but it's less than or equal to b. So, yeah, it's less than or equal to b, and that's less than 1. So x is less than 1. 1 is not less than 1. 0 is less than 1. So we've carefully proven that the limit has to be 0. There's no other choice. Okay, so a simple example using this little theorem to prove divergence of a sequence. Instead of using the definition of a limit, which is a pain in the ass to use, to prove that things are divergent. So let's do something very easy. This limit does not exist. Let's suppose it does exist. And let's look at two different subsequences. The limit exists, they have to be the same. So, yeah, let's look at the even and the odd terms. Obviously, this is 1. So in the homework, you can just say the even terms is 1, the odd terms is -1. So this is -1. Yeah, this is -1. You can't have a number being both 1 and -1. That's absurd. Okay, yeah, I guess I forgot that little square thing here. Okay, so let's prove something that not sure if we'll really need it, but it's still useful to know, useful to have. And that is the following. Another way to describe divergent sequences. Okay, so remember the definition of a limit. So we're going to negate this in a second. So by definition, it's if for any epsilon bigger than 0, there exists k. Yeah, and I'm writing this remember I wrote this in this abstract way, as I mentioned a while ago, So that I can easily negate this, going back to 299 negation that you should have done to have learned how to negate different quantifiers. Okay? So for any epsilon, there exists k, where for any n bigger than k, xn minus x in absolute value is less than epsilon. Go back to this in a minute. Okay, so we have the following theorem. So the theorem says that the following are equivalent. So given a sequence and given x, this limit is not equal to x. Now there's two possibilities here. It might be that the limit is that this sequence is convergent and just not equal to x. Or it could be this sequence is not convergent at all. Okay? We don't know. I mean, it could be either one. Two, there exists some epsilon 0, some constant, and a subsequence let's call it xnk. Not sure what happened there. There's a subsequence of my original sequence where xnk minus x in absolute value is bigger or equal to epsilon 0. All right, so let's do 1 implies 2. Okay. All right, yeah, so do careful negation. Well, it's equivalent to, but the same as, I'll do it for no way. Okay, yeah, so let me do it this way. Not really recall, but so let's negate this. Okay. So how does that work? Well, when I have a string of quantifiers, when I negate this, it becomes there exists some epsilon bigger than 0. And instead of using epsilon, usually epsilon's for all. When we have there exists, we just denote it by epsilon naught, epsilon 0, or something like that. So let's do it epsilon 0. And then we negate this here. Okay. Well, how do I negate this? Well, this becomes for all. Again, I'm just doing 299 stuff. Okay, and now we negate this. Okay. Well, how do we negate this? This becomes again, there exists. And you can also put so this really depends on this depends on k, but yeah. So this is really so let me hold on 1 second. getting confuse anyone. So we're going to negate this. So yeah, just to make clear, for any k, there exists an n depending on k, possibly, where this is true. Negate this here, that just means, well, if this is not less than epsilon, it's bigger or equal to epsilon. So just careful step-by-step negation. I think I gave this actually as extra credits in 299 when I taught it, or something like this. Probably too hard for 299, but okay. All right, so I'll just rewrite that. If there exists epsilon 0 for any n, we're for any k, there exists n bigger than k, where xn, n's not behaving well today. This is bigger or equal to epsilon 0. Okay. Again, it's really nk. Okay, so how do we get a subsequence? Well, that's pretty easy. Not a whole lot to that. So I can set k be whatever I want. Do whatever I want. Let's start off with k be 1. Pick and 1. Where this is bigger or equal to epsilon 0. Okay, yeah, like I said, this n depends on k, so we're going to call it n1, corresponding to k equals 1. Okay. All right, so now let's set k to be n1. Okay, now let's pick n2 bigger than k. So there exists n bigger than k. So n2 is bigger than k, which is n1. This is true. Just continue on, set k to be n2, pick n bigger than n2, set that to be n3, so pick something bigger than n2, etc., etc. And then we're done. We get a subsequence. It's a subsequence of there's a subsequence of x n. That satisfies what we need. X and k minus x bigger or equal to epsilon 0 for all natural numbers. Okay. Okay, so 2 implies 1 is quite a bit easier. So if 2 is true, this is true, well, let's just take the subsequence. So if we did have convergence, well, this implies, well, x has to be the limit of the subsequence, so it's kind of trivial. We proved that if x converges to if xn converges to x, and any subsequence converges to x. But this violates. What does this violate? This violates 2. You can't have convergence of a subsequence but where for all these terms it's bigger or equal to 0. Definition of convergence is for any epsilon there exists a spot where if you go further in the spot, further in the subsequence than the spot, then the absolute value is less than epsilon. Here we're saying it's always bigger than epsilon, bigger or equal to epsilon. So this violates 2. Okay, so let me prove something we'll use later on in the course. It's a very important theorem. It's if you're taking topology, you'll see that it's equivalent to compactness in topology. This is a very important concept in topology, particularly when dealing with metric spaces. So this is often called countable compactness. So this is in the context of the real number. It's called the Bolzano, Weierstrass. This is really that thing here. Anyway, Weierstrass. Very simple theorem. Proof isn't too hard. So this says if I have a bounded sequence, so every bounded sequence has a convergent subsequence. So there exists a subsequence x and k equals 1 to infinity. And x, real number x. So actually what we'll actually use this to prove the intermediate value theorem. In particular, using soups and imps, we'll get a sequence, and then we'll have to, the sequence is not going to necessarily converge. There's absolutely no reason why it would. So we'll have to do the next best thing, which is take a convergent subsequence. So that's the way I like to think about this. In various algorithms, you get sequences popping out of the algorithm. You would love it for that sequence to converge, but in general, it's probably not going to converge. So you do the next best thing and take a convergent subsequence. Okay? And these sequences that you get from various algorithms, they're often bounded. All right, so the proof is a fairly easy application of the nested interval theorem. Okay? So what is it? Okay. So let's first use the fact that it's bounded. So pick a big M. Where this is true, equivalently, minus M is less than or equal to xn. And this is for all natural numbers n. Okay. So, yeah, I'm going to use the intermediate, I'm going to use the nested interval theorem. So let's start off with my first interval, which is just minus m. So I divide I0 into two closed interval halves called I1 prime and I1 second prime. So the picture here is very straightforward. So I'll do this in general soon. So I'm going to just call this I0. Of course, this is minus m to 0, 0 to m, these two closed intervals, but anyway. So this is the first half, and this is the other half. Okay, and I want to emphasize that I want these to be closed intervals. These are two closed intervals. Okay, so where is this going? Well, let's see. So the point here is that either one of these two closed intervals, could be both, but either one of these two contains infinitely many elements or let me write it a different way. So either one of these two intervals contains xn for infinitely many natural numbers n. This is not subtle here. Okay? I have a sequence. The entire sequence is contained in I0. The entire sequence is contained in I0. So either one of these two halves has to contain infinitely many xn. Either one of these two halves has to contain xn for infinitely many n. Otherwise, I0 only contains xn for finitely many n, which is absurd. Xn is bounded. We pick a bound for xn that works for all n. So all of the xn's are in this interval. So either the left half or the right half has to contain xn for infinitely many n. Again, otherwise, this whole interval does not contain all the xn's. It only contains finitely many of xn for finitely many n. Okay. So without loss of generality, that means I don't care which one it is. Let's just say it's I1 prime. And let's set I1 and for my nested interval theorem to be I1 prime. If I2 prime does, then set it to be if I1 second prime does, then set I1 to be I second prime. I1 second prime. If both of them do, then we don't care which one you pick. Let's just say it's I1 prime. It really doesn't matter. So what does matter is the following. The length, L for the length of I1 is 1/2, because it's half of I0, either the left half or the right half. And that is, well, 2m minus m to n. Obviously, I0 is larger than I1. Being a pain. And I1 is a closed interval. Blue here. All right, so basically we just continue on. So in particular, I1 contains xn for infinitely many n. So I'm going to do the same thing. I'm going to divide I1 into two closed interval halves. And there's nothing special about halves. I mean, I could theoretically do like a third or 2/3, or I can do really funky things, but there's no point. Let's make life easier and just divide it into halves. Call this I2 prime and I2 second prime. Okay, so either one of these could be both, but at the very least, either one of these has to contain I'm not sure what's going on here, but anyway, for infinitely many n. If not, then I1 only contains xn for finitely many n. That's not true. We did this whole thing so that I1 contains xn for infinitely many n. Okay? So either the left half or the right half has to contain xn for infinitely many n. And we don't care which. What the hell, I'll say it's the right half. We just don't care one bit. Let's see what's going on. Okay. So yeah, let's say the right half does, and if both of them do, again, let's just, doesn't matter which one we pick whatsoever. Both of them do. Okay, so without loss of generality, x1 does. Set 1 second. Yes, so set I2 to be I2 second prime. So I forgot to do one thing here. So I1 contains xn for infinitely many n, so let's pick any one of those elements. Okay. We don't care what the element is. Pick one of them. Okay. So let's continue on. So what do we do next? Okay, well, yeah. I2 contains xn for infinitely many n, so let's just pick some n bigger than n1, where xn is an I2. Let's call that n, any one of that n, any n bigger than n1, where xn is an I2, let's call it n2. So I can pick n2 bigger than n1, where xn2 is an I2. So we have nested closed intervals, I0, I1, I2, where this is true, and, well, this is 1/2 length of I1. Again, L for length of the interval, just right endpoint minus the left endpoint. And that's 1/2 squared 2 to the n, 2 times n. All right, so yeah, just continue on like this. Let's do this inductively. Okay. Back it. Okay, yeah, so just make sure we're all on the same page. We're just gonna just continue on like this. So in general, let's say I'm given closed intervals all the way up to, let's say, k minus 1. Where x and j is an I j, for j equals 1 to k minus 1. So a bunch of stuff here. Forget it all. So the length of I k minus 1 is 1/2 to the k minus 1 times 2m. And crucially, each one of these ij's, for j is 1 k minus 1, contains xn for infinitely many for infinitely many. So just do exactly the same thing as before. Divide ik minus 1 into 2 halves, called ik prime, ik second prime. So picture nothing different than before. Ik minus 1, k prime, ik second prime. Pretend that this is right smack dab in the middle. Okay. Because ik minus 1 contains xn for an infinitely many n, one of these 2 halves also has to contain xn for infinitely many n. So I did the right one before. Let's just assume it's the left one. Without loss of generality, ik prime and xn for infinitely many n. So in particular, I can pick n k bigger than n k minus 1, because this contains, I can pick nk bigger than nk minus 1, where x and k is an I. Yeah. So I should say I forgot the step here. So let's set ik to be ik prime, just like before. Just forgot to write that. Okay. Ik contains xn for infinitely many n, so I can pick nk as large as I want, where x and k is an ik. All we needed is bigger than nk minus 1. Okay, so let's use the nested interval theorem. So what do we have? We have closed intervals, closed nested intervals, I0, I1, etc., etc. We have an element x and j in each ij. This is a subsequence. N1 is less than N2, etc., etc. Okay, so we keep subdividing the prior interval to get the new interval. We're dividing by half, so just like we've had before, for each j, this is going to be 1 over 2 to the j times 2m. Okay. So by nested interval theorem, so first of all, let's say I j is aj bj. Okay. So really, I'm going to use the old homework associated to the nested interval theorem. So let's say a is the so remember what a was? It's the supremum of the AJs. Supremum of the left intervals. B is the infimum of the right intervals. Then the old homework was that this intersection here, don't really, I guess we can include 0, but matter. This is A to B. Okay. That's old homework. Easy new homework is that A equals B. Okay. And that follows from this fact right here. It's going to follow from this fact right here. The length of the intervals converges to 0, trivially, as j goes to infinity. So it's going to force this to be just a singleton. So I claim, so let's call this x. Okay. So I claim that this limit here is going to be x. Why is that? Okay. Well, so yeah, so x is in each of these intervals. I'll use k. Matter. So not just x, but x and k, and x is in ik for each k. So it's an ak to bk all natural numbers k. Remember, that's the way kind of we're constructing these intervals, xnj's and ij for each j. Okay, well, I guess really you should do different cases to compare this with absolute values, but yeah, I'll just draw the picture and you can fill in the details if you so desire. So we have a, k, b, k. Don't know if x is bigger than x and k, or if x is smaller than x and k, or we don't know if x equals x and k. Whatever, they're both in this interval. Let's say we have something like this here. So that means x minus x and k is less than or equal to bk minus ak. Again, both of these are in this interval. So the distance between these 2 points is going to be less than or equal to the length of the interval. And that length is 1 over 2 to the k times 2m. And it obviously goes to 0. Okay, it goes to infinity. And that means we actually had a little kind of trivial proposition to saying if we have something like this, then that means x and k goes to x. So yeah, and that's the proof. So the book has another proof proving that every bounded sequence has a monotone subsequence. I don't have time to go through that, and I'm not sure if I've ever actually used that in my research before, and maybe once or twice. So it's good to know that's true, but I really would have to think hard if I've ever even used it, or even seen it used. Whereas this Bolzano-Weierstrass theorem, you use it all the time. I mean, you use it just all the time. I mean, a lot of times you want something like this for a metric space, and it's quite special. But yeah, you'd get more into that in topology. But all right, hopefully this video was useful. On Wednesday, we will do lim sups and lim imps. Okay, so see everyone Wednesday.